comes Kira. Okay, let me get her in if I can find my cursor. There it is. All right. Okay, Kira's here. All right. We're missing Esther, Jemanuel, and Laurent. So hopefully they will be coming in sometime soon. Okay. All right, just a few things. I don't know where you guys are. I think we talked about this before, maybe not. I've had several of you in other classes too, so I'm pretty sure that I've said it in one of your other classes. I don't remember if I said it in this one or not. But I received an email, several emails, bunches of emails, but a couple that went to all students. So I hope you have seen them. The first of these that I recall dealt with tutoring, and it was talking about the Space Center, I believe it was, but it's not just the Space Center. We also have the STEM lab that Dr. Thomas runs, and I think Student Support Services also does tutoring. So there's lots of tutoring available on campus. Now, I'm not here suggesting that y'all need tutoring. Now, if you need it, use it. I mean, by all means. But what I am suggesting is that you guys are probably the most qualified, would be the best tutors we have on campus, especially for math and science type stuff. So if you haven't thought about doing this, and especially since you may have some time on your hands, you might consider that. I mean, they pay you something, probably not a huge amount, but it is a pretty decent rate, I think. You get to choose the hours you want to do it, and this sounds really altruistic. You're helping people. But you know what else? You're helping yourself, because frankly, I learned calculus the best and the most when I was in an undergraduate. I was in the dorm system. I was a counselor, and I basically did a lot of tutoring on my hall. That's where I really learned calculus. I got the basics down in class. I got it down when I heard the professor talking and all that kind of stuff, and doing homework and stuff. But man, I had to know it when I had to explain it to somebody. Well, why is this? Well, that's when I learned calculus. So you'll be doing yourself a favor as well. Please consider signing up and consider being a tutor, and look at that email and go for it. And the other places, I'm sure you can find Student Support Services, Dr. Shawanda Thomas, the director of the STEM program. Her assistant has a email address too. So there's lots of opportunities. Please give it a shot. Okay. Number two, now this may be more directly associated with you guys. I know some of you it is. Maybe every one of you. Are y'all graduating this term, or have you got another term or so left? Okay, that's what I thought. At least some of you would be. Well, this is the time. If you haven't already applied to graduate, this is the time to do it. Go to your emails, find that email. It lays out everything for you and where to go if you have questions. I was starting to copy all that and put it on Blackboard under an announcement or somewhere like that. But I thought, hey, this is already going to all the students. There's really no reason for me to duplicate it, but I did want to announce it in class. So, and even if you're graduating next term, which I think probably most of the rest of you are, if you're not graduating this term, the odds are, I think they really encourage you to apply to graduate the term ahead. I know they did that when we were on the old system. I don't know about this new banner system or not, but you can ask them that question too. Check your emails, find out, and this is the time to do it. You don't want to wait too late and not be able to graduate. Okay, that almost rhymed, didn't it? Okay, so any questions, issues, concerns, anything else? We are now recording, but I wanted that recorded. Okay. Anything? All right. Well, hopefully some of the others will be coming in. Let me go on and get on the slideshow from current slide. All right. All right. Right now we're in Chapter 9, Infinite Series. We're in 9.1 where we're talking about sequences, and then that moves into 9.2 where we'll do series. Okay. Now you might think those are almost the same words. They're similar but not the same. Okay. What a sequence is a set of numbers, entities, individual things with commas in between. Okay, basically. It's a sequence of numbers. Okay. Now, when we get to series, those are sums of sequences. So they are related, but they're a little bit different. These are just the numbers themselves. Series will be adding those numbers together. Okay. So we're on example 8, which is on page 594. We've just been talking about monotonic sequences and bounded sequences. Actually, we talked about monotonic. Bounded is coming up next page. All right. So any questions before we get started? Okay. So it says here, determine whether each of these sequences having the given nth term, that's what they give us here, determine whether these are monotonic. Now, someone refresh my memory. What does it mean to be monotonic? Strictly increasing or strictly decreasing. It cannot be bouncing around. Okay? That's a layman's term. Okay. Actually, the way they say it is non-decreasing or non-increasing. Okay. That allows for you to have some flat areas in it. Okay. It doesn't have to be strictly decreasing. It could be constant decreasing, constant decreasing. It just can't go up and become increasing. Same thing with a increasing function. It can go up, level out, go up, level out. That would be okay. It just can't go up, come down and go up. That would not be okay. So what we have to determine here is whether each of these sequences is monotonic or not. Okay, I'm going to move my phone out of the way. It's fully charged. Get my Wacom pad here, and let's see what we've got. Well, if in doubt, pick a few points. I think we've already seen this one before. A sub 1, you know, the n is a counter. It starts at 1 and increases, okay, by 1. These are your natural numbers, n equal 1 and up. So when n is equal to 1, your a sub 1 is equal to 3 plus negative 1 raised to the first power is a minus 1. Okay, so that is going to be 2. A sub 2 would be 3 plus a negative 1 squared, because n is 2 now, and that would be 3 plus 1. That would be 4. Remember this one? The next one, a sub 3. So far that's increasing, not decreasing. This will be 3 plus a negative 1 cubed, n equal 3. Well, that's a negative 1. 3 minus 1 is equal to 2. Nope, not monotonic. It went up, down, up, down, up, down, not monotonic. Okay, that one is not. Get the gist? How about B here? Which is B. There's my pen. So B sub 1 would be 2 times 1 is 2 over, if I could add, 1 plus 1 is 2. So that would be 1. B sub 2 would be 4 over 3. 1 plus 2 is 3. That's 4/3, okay? B sub 3 would be 6 over 4, right? 1 plus, which is 3/2, okay? B sub 4 would be 2 times 4 is 8 over 5. B sub 5 would be 10 over 6, which would be 5/3. I can do them upside down. 5/3. Okay, we could go on, but let's see what's happening. 1 to 4/3, that's increasing. 4/3 to 3/2, that's increasing. 3/2 to 8/5. Let's see. That is slightly increasing, isn't it? This would be about 1.5, exactly 1.5. This would be 1.6. This would be 1.67. So yeah, they seem to be increasing. B sub 6, let's just do another one. We got room for it here. That would be 12 over 7. That's 1 5/7, right? The other was 1 2/3. 5/7, yeah, is greater than 2/3. It looks to be monotonic. Increasing, slowing down that rate of increase, but still never decreasing. All right, how about this one? C. Where is my, there it is, okay. C sub 1. That would be 1 over 2 to the first is 2 minus 1 is 1, so that's just going to be 1. C sub 2. That would be 4 in your numerator over 4 minus 1, which would be 3 in the denominator. C sub 3 would be 9 in the numerator, and 2 to the third is 8 minus 1 is 7. Okay, C sub 4 is 16 divided by 16 minus 1 is 15. Okay, I think we got a problem here, don't we, Houston? Here it was increasing, and here I think that was decreasing a little bit. Well, maybe it's hard to tell. This is 1 2/3. This is 1 2/7. Yep, that's less than 1 2/3. So it increased and then it decreased, and now it's decreasing some more. If you leave this one off, I think that would be monotonic. But with that one in there, I don't believe so. Let's see what they say. The first one alternates between 2 and 4. We saw that. Nope, not monotonic. So it's not monotonic. The second one, sequence is monotonic because each successive term is larger than the predecessor, not much, and less every time, but still always larger. Okay, and if you do the graph of it, you'll see that is indeed the case. It flattens out, but never completely goes flat. Okay, now the next one. Oh, note that because n is positive, you can multiply each side of the inequality by 1 plus n and 2 plus n without reversing the inequality sign. Okay, that's perfectly fine, but I don't know. I'm sure that tells you something, but I can't quite figure out what they're saying with it. And how about, oh yeah, okay, here's what they're doing. They're taking this, the 2n over 1 plus n, multiplying the numerator and denominator by 1 plus n. Okay, now, oh No, that's not what they're doing. Oh, they're looking at the n plus 1 term. I see what they're doing. Okay. They look at the nth term here, and then look at the n plus first term. So this would be 2n plus 2, and this would be n plus 2. Okay? So this would equal 2n plus 2 over n plus 2. Okay? Now, for any n, the numerator is greater than the denominator, obviously. So that means you're always going up. Always going up for any n. So I think that's what they're meaning. Oh, and that's b to the n plus 1, of course, yeah. And that's what we just did. Okay. Now what did they just do though? They multiplied okay, this was the denominator we had here, m plus 2, and this was the denominator they had here. So they put it over least common denominators, I think. 2n times n plus 2, that would be right, and this would be 2n plus 1, 2 times n plus 1 times n plus 1. Which is what they've got here. They've just written it in a strange form. Okay. Now the question is the left-hand side always less than the right-hand side? Well, that would be 4n. Boy, this is a long, crazy way to do it, but okay. And is that greater than this? Well, looky here. This is 4n plus 2n squared. This is 4n plus 2n squared. This is 2 more, always, always, always than the left-hand side. So yes, that's increasing. Okay, 0 is less than 2. Good deal. Starting with the final inequality, which is valid, you can reverse the steps and conclude the original inequality is also valid. It's always the left hand is less than the right hand. Okay, now C, the sequence is not monotonic because the second term is greater than both the first and the third term. They make it seem like the problem is the second term. I contend that the problem was the first term. If you took the first term out, if I could find my, if you took the first term out here, I believe the rest of those would then be monotonic. I didn't do them all, but it sure looks like it's heading down that way. But they say, oh, that's the bad guy because, but not really. This is the bad guy. If you take that one out, then it would be a monotonic sequence. But it isn't the way it's written. Okay? Note, if you drop the first term, the remaining sequence is monotonic. But that first term was part of the sequence. So that threw it out. So they said the same thing I did. All right, now let's go to what we mean by bounded sequences. Monotonic sequences and bounded. What is we mean by bounded sequence? A sequence A sub n is bounded above when there is a real number m such that A sub n is less than m for every n that you put in here. Okay? That number m is called the upper bound of the sequence. Now, I would have phrased that the least number m for that's true would be the upper bound of the sequence. Okay. A sequence A sub n is bounded below when there is some real number capital N such that n is less than or equal to A sub n for every little n that you have there. That number capital N is called the lower bound of the sequence. And again, I would say the maximum of those capital N's would be the lower bound of the sequence. Yeah, they're getting away with it because that an upper bound or a lower bound. If they want to say what is the least upper bound or the greatest lower bound, then that would be a "the" there. Okay. A sequence A sub n is bounded when it is bounded both from above and from below. So that's our definition of a bounded sequence. Okay. One important property of the real numbers is that they are complete. Now, I don't know if you remember this from way in the past. Important property of real numbers, they are complete. Informally, that means there are no holes or gaps in the real number line. They completely cover everything. The set of rational numbers does not have that completeness property, because you can come up with all kinds of rational numbers, but somewhere in between 1.4 and 1.5, those are both rational numbers, you can have the square root of 2, which is a 1.4141, blah, 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 blah. Okay? And you can keep narrowing it down with rational numbers, but you'll never, ever be able to complete, and have that square root of 2, because square root of 2 is irrational. Okay? There's always going to be some holes there. The completeness axiom for real numbers can be used to conclude that if a sequence has an upper bound, then it must have a least upper bound. That's what I was talking about. That's an upper bound that is less than all the other upper bounds for the sequence. I'd say less than or equal to. Okay? And similarly, well, here we go. For example, the least upper bound for this sequence, a sub n, is equal to n over n plus 1. Well, that would be 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, 6 over 7, 7 over 8. Okay, that is a monotonic sequence. 1/2 is less than 2/3, 2/3 is less than 3/4, 3/4 less than 4/5, 4/5 less than 5/6, and on and on and on. It's monotonic. And what's the least upper bound? Well, an upper bound would be 25, of course. Yeah, nowhere, never getting close to 25. The least upper bound is 1, because it's getting closer and closer, but will never, ever, ever reach 1, because the denominator is always 1 more than the numerator. So 5,464,815 over 564,816, that's still less than 1, but 1 is its upper bound. Now, they talked about least upper bound here. Theorem 9.5 says bounded monotonic sequences. If a sequence, a sub n, is bounded, now they mentioned the upper, they didn't mention the lower. Bounded also means it has a greatest lower bound. It has to have a least upper bound and a greatest lower bound, and monotonic, then it converges. Okay? So here's example 9. Yeah. Here's a sequence. A sub n is 1 over n. Okay? Now, if you start plugging in n's there, 1 over 1 is 1, 1 over 2 is 1/2, 1 over 3 is 1/3, 1 over 4 is 1/4, 1/5, 1/6, 1/7. Okay. It's bounded. Okay. Number 1 is monotonic. Every one of those numbers I said is less than the previous one. 1, 1/2, 1/3, 1, yeah. Or you could do it this way: 1, 1/2, 1/3, 1/4, 1/5, 1/6. Okay? It's bounded above, yeah, but more importantly, it's bounded below. Okay? And it's bounded by the number 0. Because guess what? That thing's never going to be negative. But it's getting closer and closer to 0, never reaching 0, but it is, but never goes negative. So it's bounded below by 0. It is monotonic, always decreasing. By the theorem, it must converge, and it does. Here's another, a divergent sequence. B to the n is n squared over n plus 1. Well, let's just take a few. 1 over 2, that would be your first one. 2 over 3, that's the next one. I'm sorry, 4, right, 4 over 3, that's the next one. 9 over 4, 16 over 5, 25 over, did I leave out? No, over 7, I think it was. Wait just a second. Never mind. Okay. Now, yeah, my roll book just collapsed, dropping papers everywhere. Hold on just a minute. Let me get things. All the king's horses. Okay. Well, everybody's not here, but sorry. I'm going to put my roll book off to the side here so it won't be falling again. Okay. This is monotonic. It is increasing. N squared goes up faster than n plus 1. Always, okay, even from the very get-go. Okay, it is monotonic, but it's not bounded from above and below. It is bounded below. Nothing is any less than 1, okay? In fact, 1/2, I'm sorry, 1/2, because the first number was 1/2. But it's not bounded from above. So therefore, it has to be bounded both, remember? And so this is not bounded, so it's certainly not convergent. Okay. Now, we have actually proven that part. Let's go back to the theory here. If a sequence A sub n is bounded and monotonic, then it converges. What we didn't say, if A sub n is, I would say if it's unbounded, it can't be converging. Okay. Goodness gracious, this thing keeps making. Okay. So a lot of times these statements like this will go one way, but not necessarily the other way. And I can't think of a counterexample now, but hold off. You can't always, I was just about to do it and say, therefore it doesn't converge. It doesn't. I guarantee this, but I don't think we can say it just because it's not bounded. I think maybe we can. Okay. Now, the divergent sequence C sub n, which is -1 to the nth power, is bounded, but it's not monotonic. And guess what? It's not going to converge, but you can't guarantee that will always be the case. In this case, it won't. I can think of some examples that are not monotonic, but actually are getting closer, so they are converging. Okay, so just because it's bounded and not monotonic, you can't say it doesn't converge. That's not what the theorem said. It said if it is bounded and monotonic, it's guaranteed to converge. It doesn't say the negative of that. So you have to be careful with that. Whoa! And they have that being the last slide in the slide set. And that indeed is. Okay? So let me give you homework exercises here. Now, I've been tending to skip the concept checks. Those are good things for you to look at. They're always at the very first part of the exercise set. I skip them because that's not something that I count as a homework problem, but those are really good things for you to look at, you to think through, make sure you understand before you do the homework, because otherwise they are important in getting the answers. So homework exercises would include any of the odds 5 through 9. They're all at Calc Chat. 9's at Calc View. Do number 11. It's a Calc Chat. Now I would try to do all 4 of 13 through 16. They're matching the figures with the sequences, and you can only the odds are going, 13 and 15 are going to have answers in the back, but I think you can match those up pretty well. And only the odds will be at calcchat.com too. Then either do 17 or 19, they're both at CalcChat. 21 or 23, both at CalcChat. 21's at CalcView. 25 or 27, both at CalcChat. Any of the odds 29 to 43, they're all at CalcChat. 29's at CalcView. Any of the odds 45 to 51, they're all at CalcChat. 49 is at CalcView. Any of the odds 53 to 59, they're all at CalcChat. 53 is at CalcView. 61 or 63, both at CalcChat. And then do any of the odds 65 through 75. They should all be at CalcChat. Any of the odds, either 77 or 79, they should both be at CalcChat. Those are true false. And then 81, I'd say any of the odds 81 through 89, they should all be at CalcChat. But time out for a moment here. Look at 81. That's talking about the Fibonacci series. And I didn't know it from the progeny of rabbits, okay? This guy was really ancient, early mathematician, 1170 to 1240. We don't know the exact ages, dates of his birth and death, but those are approximate. He was a brilliant mathematician, I think pretty clearly, I believe, Italian. And this was probably one of the times when Italy was probably one of the top countries around. He was quite a traveler. I think his father was quite wealthy, so he got to travel around. He got to interact with the Muslims, who had kept a lot of learning alive when Europe was in the Dark Ages. He may have made it even as far as India and met with some of those people, other Middle Eastern people, and just throughout the world. I think his dad was in shipping or something like that. So he was a brilliant guy, had lots of opportunity, and he came up with this sequence. That is a very interesting sequence. It's not your normal one. All you can do it is define it sort of recursively. There's not a, you can't say f sub n is this, you know. You have to do it based on what the previous f was, okay? But it is used in an enormous number of applications. Nature uses it all the time. The seeds in a sunflower, the shape of a cockle shell, you know, a seashell. There are just tons of places where the Fibonacci sequence shows up in nature. One of the most beautiful buildings ever built was a Parthenon in Greece, and it was done exactly according to Fibonacci's number pattern, and it just made it so pleasing to the eye. Others, like I think Leonardo da Vinci, used it a lot. Okay, so there's a lot there, including talking about the golden ratio. There's at least one, maybe several paper topics right there. If anyone's interested in it, hint, hint, be working on your research papers. Okay, enough of that. Let's move on to 9.2. Okay. Now, let me find, there's 9.2. Okay. Now I've got to go back through and move my taskbars around, toolbars, whatever you call them, to get them out of the way again. Okay. And we'll go from current slide. All right, chapter 9, still talking about infinite series. This time we get into series. Before we're only talking about sequences, now we're talking about series. Not just series, but also series and convergence of series. Okay? Now, objectives here: understand the definition of a convergent infinite series. We'll use properties of an infinite geometric series. There's a very special kind of infinite series. And we'll use the nth term test for divergence of an infinite series. Now, if you think about it, we kind of did something like an nth term test for a sequence. Sequences are usually a little bit easier, I want to say that, but it's not quite true, to determine divergence or convergence. Sort of. Okay? Now, as I said, there are connections, very definite connections. Actually, connections from both ends, and we'll see what I'm talking about in a minute. So what do we mean by an infinite series? One important application of infinite series is representing infinite summations. I'm sorry, of infinite sequence is representing an infinite summation. Informally, if a sub n, that's how we represent sequences, is an infinite sequence, okay, then the summation of those numbers a sub n in that sequence is what we call an infinite series, or an infinite summation. Infinite series is what we usually call it. Often we just say a series. Okay, so a sequence is a listing of numbers that have a pattern to them, somehow a pattern. The infinite series, or a series, is a sum of a sequence. Okay, now just because a sequence converges, the sum of that sequence may not, because you're adding things to it every time. Now there may be a little bit of your gut feeling say, whoa, if I'm adding something every time, how could it possibly converge? It can. Okay, we'll get to that in a bit. Now, in this example here, a sub n was an infinite sequence, and this was your first term, your second term, your third term, your fourth term. That's an infinite sequence. When you add them together, a1 plus a2 plus a3 plus a4 plus all the way up, then you get your series. The terms, the numbers a1, a2, a3, and so on are called the terms of the series. That's what we called things separated by plus or minus signs always are called a term. There's just no variables in these, okay? But that's what we've always called them. For some series, it is convenient to begin the index at n equals 0 or some other integer. We didn't typically do that with sequences, but we do allow ourselves, give us permission to do that with series. Okay? As a typesetting convention, it is common to represent an infinite series as the summation of a sub n. Now notice what they haven't done. They didn't say where to begin this sequence. Here that was n equal 1, series n equal 1, and it didn't say where to end it. That's almost always infinity. Okay? But that's how, and if it's an infinite series, it will be infinity. So the upstairs here is going to be infinity. What we don't know what n is starting. It could start at 0, it could start at minus 3, it could start at 12, it could start anywhere, but then go on from there. Okay? In such cases, the starting value for the index must be taken from the context of the statement. Now, like I said, a series is a summation of a sequence. Okay? But not just that. That's not the only connection between sequences and series. Here's the second one. If you start adding an infinite series, now certainly you can't add them all. I mean, it's infinite. You do it till the cows come home, you still wouldn't be through. Okay? But what you do consider is a partial sum. S sub 1 is just going to be the first of that sequence, a1. S of 2 would be the second, A1 plus A2. S of 3 would then be A1 plus A2 plus A3. S of 4, A1 plus A2 plus A3 plus A4. S of 5, A1 plus, you get the idea. Keep on going till you get down to the nth partial sum, which will be A1 plus A2 plus A3 plus A4, all the way up to A sub n. Okay? Now, guess what that forms? That forms a sequence of numbers. Okay? Because these are just numbers here. The partial sums are numbers. And you're not adding them together, you're just looking at those numbers. If that sequence of partial sums converges, then the series is said to converge and has the sum indicated in this definition. So you see, we started with a sequence, added them together, got a series, and then, but didn't add them all together, added partial sums of them, that gives you a new sequence. Okay, and if that sequence converges, the second sequence, the sequence of partial sums, then the series converges. So here's the definition. Definitions of both convergent and divergent series. For an infinite series, summation n equal 1 to infinity, though you understand this could be something other than 1, of a sub n, the nth partial sum is S sub n, that's what we give it, capital S sub n, is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, all the way up, but stopping at a sub n. This last term in that sequence, added to all the other terms in that sequence, gives you a series, but this is a partial sum of that series, and that then produces a sequence of these partial sums. It almost feels like you're going in circles, and you kind of are. If a sequence of partial sums, and this again is a sequence, there's the symbols for it, converges to some number S, cleverly disguised, then the series summation n equal 1 to infinity of a sub n converges. The limit S is called the sum of the series. Okay? And if you were to add them all together, it's going to get closer and closer and closer and closer and closer to that number S. If that sequence of partial sums diverges, getting bigger and bigger, or smaller and smaller, you mean negative and negative, then we say it diverges. Okay, excuse me just a second. I tried to cram down as much lunch as I could in less than the 30 minutes that I had. So I didn't drink enough, so my throat's awfully dry. I had a Zoom meeting with the dean at 9, and then I've been in class ever since. Okay. So here's example 1. This, by the way, is on top of page 600. Okay. Here's a series. The summation, n equal 1 to infinity, of 1 over 2 to the n. So 1 over 2 to the n would be how we would name the sequence, but this is a summation of that sequence, so that would be 1/2 plus 1/4 plus 1/8 plus 1/16. Every term is 1/2 of the previous term. So 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1/28 plus 1/256 blah 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 blah. So it has the following partial sums. Of course, the first partial sums is just 1/2. Second partial sum will be these two added together, which will be 3/4. Okay. The third partial sum will be these three added together. In other words, 3/4 plus 1/8. Well, 3/4 is 6/8 plus 1/8 is 7/8. So that would be 7/8. Okay. The fourth partial sum would be 7/8 plus 1/16. Well, 7/8 would be 14/16 plus 1 is 15/16. So there's, and you keep on going until you get 1 over 2 to the n. It's the sum of all those. Now, just the fact that this certainly is converging to 0, I'm sorry, 1 over 2 to the n converges to 0. We know that. That doesn't guarantee that this sum, because you're adding these things together. You can't guarantee that's also going to converge to some number. Certainly not going to converge to 0 because you're adding something in 1/2 and they're all positive numbers, so it's never going to get to 0. Is it going to get to anything else? Okay, well, looking at this, we seem to think yes, because the next one was going to be, as I said, 15/16. The next one was going to be 31/32. The next one would be 63/64. The next one would be 1/27, 1/28. So absolutely, that's partial sums is converging to the number 1. We'll never, ever, ever quite get there, but is converging to 1. Now, here's another way you can look at this. And this may seem a little bizarre, but it is, for this one, it's true. Let's just take the number line. I can't find my pen. There it is. Okay, so here's the number line. It's supposed to be a line. It's sort of wavy for a line. And let's just take from 0 to 1. Okay, well, 1/2 is exactly halfway in between there. And that's what your first partial sum was. Second partial sum, you're going to add to that halfway between this one, which gets you here, which would be 3/4. And the next partial sum, you're going to add to that 1/8, which is going to get you to 7/8. And then you add to that 1/16, and that gets you to 15/16. See what's happening? You're getting halfway the way to 1 from where you are every time. It's going to take much more smaller steps there. You will, but you'll never get there. You only get halfway there every time. Okay, so yeah, it's going to 1, approaching 1, and that's the limit of those partial sums. Okay, here is what we just said is 2 to the n minus 1 over 2 to the n. This was 2 to the first minus 1, that's 2 minus 1 over 2. This is 2 to the n, that's 4 minus 1 is 3 over 4, 7 over 8, 15 over 16, 63 over 64. It's always 1 less than the 1 in the denominator. Okay, now that was fairly easy that way, kinda, to see, because that limit, and this can be done pretty easily, 2 to the n over 2 to n is 1, minus 1 over 2 to the n, that's rapidly going to 0, that does converge to 1. Okay, it follows that the series converges and the sum is what it converges to, which is 1. Now, here's the B part. This is still example 1. Here's the nth partial sum of a series. Okay, it's 1 over n. Here's the series. Excuse me, the summation of n equal 1 to infinity of 1 over n minus 1 over n plus 1. Okay, so the first one would be 1 minus 1/2. That would be 1/2. Okay, the second one would be plus 1 over 2 minus 1 over 3. The next one, 1 over 3 plus minus 1 over 4, plus 1 over 4 minus 1 over 5, plus 1 over 5 minus 1 over 6, and on and on and on and on like that. Now, here's the good news here. Looky here. Here you're subtracting a half from this term on the first one, but that becomes your first term here, which you go back and add again. You subtract that one and add that one. Subtract this one and add that one. You just do that all the way down the line until the very last term is that 1 that you had to begin with minus 1 over n plus 1. Well, guess what? I think, well, it's not quite the same as the one above, but it's awfully close. Okay? And that sure enough would be this partial sums, because 1 over n plus 1 is definitely going to 0 as n goes to infinity. So this is getting closer and closer to 1. Because the limit of s sub n is 1, the series does converge, and the sum of that series is 1. All right, hold on just a minute. Oh, my head is really clogging up on me. Okay, sorry. Here's another one. Here's a series. The series is n equal 1 to infinity of 1. So that's 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Do you think that converges? No way. Because every sum is 1 more than the previous sum, is 1 more than the previous sum, is 1 more than the previous sum. No way that's ever going to converge. It diverges because the sum of these is n, and as n goes to infinity, n goes to infinity, the sum goes to infinity. The sequence of partial sums diverges. So that one will not converge, ever. Now, the one we did just a little bit ago was called a telescoping series, because the second term here becomes the first term of the next sequence. So the 1/2 go away, the 1/3 go away, the 1/4 go away. So you're only left with the first one and the last one, whatever that happens to be. Okay? That's telescoping series. Notice that B2 is canceled by, you subtract B2 here, add B2 there. Subtract B3 here, add B3 there. Subtract B4, add B4. Subtract B5, add B5. So all you're left with is B1 minus that very last B that you have. Okay? So that's a telescoping series. Because the nth partial sum of that series is B1 minus, I think that's supposed to be, no, okay. Nth partial sum is that B1, the first one, minus whatever the last one was, which is B of n plus 1. Because remember, the ith term, the nth term, is the second term is always 1 over n plus 1. So this will be B1 minus B to the n plus 1. It follows that a telescoping series will converge if and only if B sub n approaches some finite numbers and goes to infinity. Moreover, if the series converges, then the sum is simply B1 minus whatever that limit is of that last term. Okay, I'm going to have to get another sip of something. Let's just see where we are now. Okay, they're skipping example 2. So before we hit example 2, sorry, I don't know, either something at lunch didn't agree with me, or like I said before, I just didn't drink enough. Let me try water. That doesn't seem to do any good. Hopefully that will. ease things a little bit. Okay, so let's move on to example 2, which is the top of page 601. So I'm going to get the book in my lap. It's heavy, and I just noticed, oh okay, for some reason everything on my desk decided to move way back to the back. Okay, let's do example 2. So I think what we'll need to do is go to the goodness, I can't talk, the whiteboard. And here, sorry, I shouldn't have put all this in my lap yet because I got to move. You can't see it, but that's a toolbar, another one that's in my way. And then also the whiteboard itself can scoot somewhat to the left and a little bit up. That gives me the maximum white space I can get. Alright. Oh man, this book's heavy. Find the sum of this series. The summation of as n is equal to 1 going to infinity, that's what it calls an infinite series, it doesn't look like one, of 2 over 4n squared minus 1. Okay, now what we can do, if you wanted to, is, of course, I think the easiest thing to do is yank that 2 and get it out of there. Okay, put that in front of the, where is my, there it is. Take this on the outside because that's always going to be a 2. Nothing's going to change when you change the ends. So let's pull that on the outside. That would be 2 times the summation of n equal 1, I can't write, going to infinity, of 1 over 4n squared minus 1. Okay, I'm going to get rid of this book. Oh man. Suddenly I feel like I've been hit by a truck or something. I've got so many wires here. The headset wires, my Wacom wires, they're just getting all tangled up here. Okay, let's write what some of this is. Remember the 2's out front here. And then this sequence, the series would be 1 over, when n is equal to 1, that would be 4 times 1 squared, which is of course 1. 4 times 1 is 4, minus 1 is 3. Okay, plus, and then 1 over 4 times 2 squared, be 4, 16, minus 1 is 15. Plus 1 over 4 times 9, 36 minus 1 is 35. Plus 4 times 25, 100 minus 1 is 99. Okay, now that's not, in my mind, particularly all that instructive. Okay, just some really big numbers here. Okay, now there's no telescoping here. And least common denominator seem to be out of the question. Did I write the problem down right? I think so. All right. So what they do, rather than what I did, is let's look at the nth term and the n plus first term, I think is how they do it. Okay. Or just look at the nth term. Now they left the 2 in there. I'm going to go on and take it out. The nth term, if I get on the right pad here, is 1 over 4n squared minus 1. This is what I should have paid attention to. Okay. Well, that looks like, just like we did with integration, we can do a partial fraction with this. A over 2n plus 1, because this factors to be 2n plus 1 times 2n minus 1 plus b times over 2n minus 1. Okay? Now, this is the nth term, always, wherever it is out there. Okay. Now, remember the trick we used. We multiplied everything on both sides by 2n plus 1 times 2n minus 1. Multiply this by 2n plus 1 times 2n minus 1. Have to write slowly or the ionizing pen just gets lost. 2n plus 1 times 2n minus 1. Okay, when you do that, of course, the denominator goes away here with that. Here, part of that one goes away, and here, part of this one goes away. So you're left with, because this factored to be that, 1 is equal to a times 2n minus 1 plus b times 2n plus 1. Okay? Now, remember the trick we used here. Let's pick an n that's convenient, like n equal 1/2. Okay? If n is equal to 1/2, you get a 1 here because there's no n there, is equal to, but n equal 1/2, put a 1/2 in here, the 2's go out and leave you 1. 1 minus 1 is 0. And this will give you, remember n is equal to 1/2. So 2 times 1/2 is 1, plus 1 is 2, so that's equal to 2b. So b is equal to 1/2. Now that's just happenstance. It happened to be what your n was. Let's choose the other one of n equal negative 1/2, because then we'll get rid of this one. N equal negative 1/2, that would be 2 times negative 1/2. That would be a minus 1 plus 1 is 0, so that goes to 0. And then this would be 2 times negative 1/2 would be negative 1 minus 1. That would be a minus 2a. 1 is equal to that. So that should be a capital A. Sorry. Sorry about that. All right. And that would yield that A is equal to negative 1/2. Now I see why the 2 was there. Okay? Because what we had, 2 times this would then have been, if we had had the 2, where is my pen? I can't find it anywhere. There it is. Okay. If we had had the 2 here, then these halves would go away. Okay. And anyway, you have not feeling well. This would be a was minus 1 1/2 over 2n plus 1 plus 1/2 over 2n minus 1. And that's equal to, that is this part, multiply 2 by that, and then you lose the halves here. So what you have, this n plus first term here, if I had left the 2 in there, that would have been 1 over 2n minus 1 minus 1 over 2n plus 1. Now that is a telescoping series. If you put the 2 back on top here, so this would be the nth term would be that. So let's rewrite this as the summation of n equal 1 to infinity of this sum, which is telescoping, however you say it, 1 over 2n minus 1 minus 1 over 2n plus 1. Alright, now let's write those out. When n is equal to 1, this will be a 1 minus, and this would be a 1/2, right? No. 1, goodness gracious, my brain's not working. 2 plus 1 is 3. 1 minus 1/3, and that gave us our 2/3 here. Okay, the next one would have been plus, and when you put a n equal 2 here, that gives you 1/3 minus 1/5, right? And that would have been, plus a 1/15. So anyway, that's what you're doing. So ultimately, your final answer is 1 minus 1 over 2n plus 1. That last one is n is going to infinity, and that would be going to 0. So it looks like it converges, yeah, and that's what I get to 1. Okay? Now, I need, for some reason, I'm just cannot quench my thirst. I don't know if it's how I eat lunch or what. All right, let's end that and go back to the PowerPoint. Okay, 9.2. And we'll go from current slide, which is that one. Okay, and let's go up to the next topic they're hitting here is geometric series. Okay. Now, in 1A back there, if you remember that one, that was a geometric series. I pointed out when I said it, every term was 1/2 of the previous term. That was just an easy way to do the terms. So in general, a series like this one, the summation of n equal 1 to infinity of 1 over 2 to the n. That would be 1/2 when n is equal 1. That would be 1 over 2. When n is equal 2, it's 1 over 4. When n is equal 3, it's 1 over 8. When n is equal 4, it's 1 over 16. That's a geometric series. In general, the series, and this is any old series, now they start it with 0 usually. Again, you can do either 1 or 0, but for the rule here, it works pretty well for it to start with 0. N equals 0 to infinity of a. Now a here is a constant multiple. You didn't have a constant multiple here in this one. We did in that last one when it was a 2 and I wanted to pull it out, okay, but that wasn't a geometric series. R to the n, okay? Now what we mean by that is you have some ratio that you're raising to a power, okay? Now your a here in this one is 1, okay? And your ratio is 1/2. That's your r. And the first term would be 1 times 1/2 to the first power, which of course is 1/2, plus 1/4 plus 1/8 plus 1/16. The 1 times each of these. So that's a geometric series. What makes it that is you have a ratio here that every term is that ratio times the previous term. A times r is AR times r is AR squared plus r is times r is AR cubed all the way up to AR to the n. That's the nth term. Okay, now this is good as long as a is not 0. Please don't ever make your a 0. You just don't have a series at all. You just have 0. Okay, so don't do that. Okay, that's a geometric series. Okay, with the ratio r, and again, r is not equal to 0. If r is equal to 0, you just have a series of zeros, and that's not very interesting. So here's your theorem 9.6. Okay, I'm sorry, my wires are still getting all tangled up. A geometric series with a ratio r diverges when the absolute value of r is greater than or equal to 1. Surely, if this is 1 or more, you're never going to converge. Ever. Ever. Because every term is larger than the last one and you're adding to it every time. Okay? But if the absolute value of r is less than 1, then the series converges always. And what does it converge to? Believe it or not, is something as simple as a over 1 minus r. As long as that r, absolute value of r, is less than 1. Because then, if the absolute value of r is less than 1, 1 minus r is going to be a positive number less than 1. And then, if you're dividing by that, you're multiplying by the reciprocal of that, multiplying your a, that constant multiplier, by that reciprocal. Okay. So here's, oh man, a geometric series. Okay. The summation, n equals 0. Again, most of the time geometric series start with n equals 0. 3 over 2 to the n. Okay. Now hopefully you see your a in this case is your 3. That never changes. So that's 3 times, and what do you have left? 1/2 to the nth power. There's your constant ratio, 1/2. Okay? Less than 1. So this is going to converge. And since we know it's going to converge, what does it converge to? It converges to a over 1 minus r, which is 3 over, I should have put an r there, 3 over 1/2, which is equal to 6. Okay? I'm guess what page we're on? Yep, 6. Okay. Now, the ratio here, like I was, oh, okay, they wrote over mine. 3 times 1, when n is equal to 0, 2 to the 0th is 1, so that would be 3 plus 3 times 1/2 plus 3 times 1/4 plus 3 times 1/8 plus 3 times blah, 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 blah. The ratio R is 2, is 1/2. The A is 3, so your geometric sequence, goodness gracious, geometric sequence, and the R is less than 1, 1/2 is less than 1. The sequence does converge. The sum is A over 1 minus R, which is 3 over 1 minus 1/2 is 3 over 1/2, which is 3 times 2 is 6. And there, for some reason, they drew the graph, which is perfectly fine. Okay. Before we do B, I swear this is so bizarre. I gotta drink something else. You folks that that are in the differential equation class, which is going to follow, you better believe I'll be going to the restroom between classes here, because I have been drinking like crazy in here. So here is another geometric series. This is summation n equal 1 to infinity. Why did I put this in my lap? I don't need it. They've got it written here. And this is 3/2 to the nth power. Notice the 3 and the 2 are raised to the nth power. If this 3 had been outside here, it's only 1/2 raised to the nth power. That's what we had last time. Not I got that this time. Now it's 3/2 to the nth power. Well, this is 1 plus 3/2 plus 9/4 plus 27/8. No way that is going to converge. Why? The ratio is 3/2. That's what's being raised to the power. And that's greater than 1. This is exploding, getting very, very big, very, very quickly. And you're adding. Each term is getting bigger, and you're adding the terms together. It's exploding. Because the R is greater than or equal to 1, definitely greater than 1, this series diverges. So, here's, let me make sure they haven't skipped any. That was 3A and B. They're skipping example 4. So let's us do example 4. This time I do need the book in my lap and my Wacom in the lap. So let's back up one slide. How are we doing time-wise? Whoa! Wait. No. We go to 155, don't we? Yes. Yeah. Okay. My last class ends at 11:40, so I always tend to think this one ends at 1:40. It doesn't. And if I'm not mistaken, some of you were in a class last spring that I made that mistake, and y'all were very quiet and let you go like 30 minutes early or 20 minutes early or something like that, and did not say a word. Okay. I remember you guys. Okay. Here's example 3. No. We've done example 3. We're looking for example 4. My Wacom was covering it. Now, by the way, this one, even though they don't show it on the PowerPoint, it is shown at larsonprecalculus.com, so you can go there and see an interactive version of this type of an example. So it says, use a geometric series to write this number. Oh, I'm sorry. Let me get my whiteboard up. Alright, and let's clear the writing out of there. Now, they say use a geometric series to do it. I'm going to do it an easier way. You can do the geometric series, certainly can. Read the book, but I want to show you how to do this the easy way. So here is a repeating decimal, and you may have done this sometime long time in your past. 0.08. And what they do, they put a bar over that. That means this decimal is 0.080808080808. I mean, that's it. You just repeat those two digits till the cows come home, forever and ever and ever. That's a repeating decimal. And it said, use a geometric sequence to write it as a ratio of two integers. Here's the easier way. Okay, since the repeating digits, okay, number one, you don't have any digits in front of the repeating digits. You could. This could have been a 0.7240808080808. In that case, multiply by 1,000 to get rid of the 724. Not get rid of it, but move it out of your decimal. Now we don't have anything in front of it, so all we do is multiply by 100. So okay, let's let this equal, didn't leave myself enough room. Let's say this is equal to y, okay? So I'm going to multiply both sides of this equation by 100. So 100y is equal to, and if you multiply by 100, that must move your decimal two places. So that would be 8.08 repeating forever, right? Now let's just subtract those two. This will give you 99y is equal to 8. Divide both sides by 99. And there's what your y is equal to. Y is equal to 8/99. Okay? Now, they do a geometric sequence, which is perfectly fine. It's correct, but it just sort of is an extra pain in the neck to have to do all that. Okay? And if you have a calculator, pull out your handy dandy calculator and see if that's the correct answer. Okay? Uh, 8 divided by 99 equal 0.08080808080808. Okay, that is exactly what we had to begin with. I don't know if you remember doing this sometime back in your long past when you used to convert fractions to decimals. This was how you converted decimals to fraction, especially if it was a repeating decimal. That's what you did. So do the thing in the book or go to larsonpcalculus.com, see how you use the geometric series for that. But frankly, it's just so easy to do it this way. Now there is a little blurb at the bottom of the page on a remark. And I don't see anything wrong with it, but it's just it says in words, theorem 9.6 states that the sum of a convergence geometric sequence is the first term of the series, I keep saying series divided by the difference of 1 and the ratio r. That's just semantics there. I don't know. So let's move on back to the PowerPoint. From current slide. All right. And that takes us to theorem 9.7, top of page 603. Okay, let me put some of this stuff out of my way for a bit. Okay. Properties of infinite series. This is theorem 9.7. Let's let the summation of a sub n and the summation of b sub n, both be convergent series. Okay. Let capital A, capital B, and little c be real numbers. Okay. If the summation of a sub n is equal to a, that is a convergent series, so it has to have a limit, what it converges to. Let that be a. So it's not just any old real number. A is that sum. B is this sum. Okay? Then the following series converge to the indicated sums. If you have the summation of n equal 1 to infinity of c a sub n, no matter how big c might be, it's still going to converge, and that'll be that big number here. Basically what you do, pull the c outside the summation, because it's just a constant. It's not varying with n at all. Pull it outside, and then what you have left is capital A. So you have c times capital A. So there's the first. That's your scalar multiple rule. Okay? Here's your summation rule. The summation of n equal 1 to infinity of the sum of these sequences a and b is the sum of their sums, a plus b. And hopefully that makes sense too. In other words, you can distribute, you might say, the summation symbol across both of the things, and this will be summation of a sub n plus the summation of b sub n. Summation of a sub n is a, summation of b sub n is b. Okay. And then number 3. Same type deal, only with a difference. Same deal. Sort of like you distribute the summation sign across the two. It's kind of what you're doing, and that would be a minus b. So if you know a sum already, then you don't have to go through all the agony of finding that sum again when you're adding or subtracting things you already know. So that was 503, the top of page, goodness, I can't read. So top of page 603, theorem 9.7. Now we move to the nth test for divergence. Nth term test for divergence. Okay. Now remember, when we're talking about sequences, if that nth term was getting small fast enough, the nth number in the sequence is getting small fast enough, we said that sequence was converging to whatever, wherever that was heading. Okay? Well, now those are becoming the terms in your series. So we're going to use that nth term as a test to see if we can tell if that sequence, as that series, converges or not. So here's what it says. And here's the first of those, 9.8. The limit of the nth term of a convergent series. Now this is telling you this series converges. If the summation of n equal 1 to infinity of a sub n converges, then this is guaranteed to happen. That means that the limit as n goes to infinity of a sub n has to be 0. Okay? Because this has to be, the nth term has to be going to 0. If that nth term is going to even something as small as 0.01, okay, then you're adding to some partial sum another 0.01, then another 0.01, then another 0.01. Guess what? Not ever going to converge. So this has to be, if that series converges, you has to be that the nth term has to be going to 0. The limit as n goes to infinity. Now, this is one of those cases. Please don't turn this around. Just because the nth term is going to 0 does not guarantee convergence. This only is a one-directional theorem here. And what they say here, the contrapositive of this provides a useful test for divergence. This nth term test for divergence states then that if the limit of the nth term, this is what I said, does not converge to 0, the series must diverge. Okay? Must diverge. If the limit as n approaches of 0 of the nth term is, n goes to infinity, of the nth term is not equal to 0, guaranteed that series diverges. Guarantee. You don't have to do anything else. If that nth term does not go to 0, that's going to be diverging. Now, I think this one also, you can't do it the other way. You can't say if this is diverging, that guarantees it doesn't. No, it doesn't. But if that nth term is not 0, the limit for that is not 0, then there's no way this is going to converge. It's going to diverge. So here's a series. Okay, the summation of n equals 0 to 2 of 2 to the nth. Okay, now you could do this several different ways. Okay, and the first is just looking at it and saying, look, there's no way the nth term of this, as n is going to infinity, is getting bigger and bigger and bigger and bigger and bigger. So that's got to be diverging. Another way you could look at it, that's a geometric series where the r is equal to 2. That's greater than 1. That guarantees it diverges. So there's just tons of ways you can look at this one and know that it diverges, because the nth term is getting bigger and bigger and bigger. Not going to a small number, it's exploding. So the sum has got to be exploding. So the limit of the nth term is not 0, the series has to diverge. That's a guarantee. Now, how about this one? Uh-oh. This is n factorial over 2n factorial plus 1. Okay. Now, these are a bit harder to deal with. Okay. And they just write it down here and don't, I think that leaves a lot to be desired. How can they just write that down and say, this is what it is? Well, here's a way to do this. What we're going to do is take, if I can find my pen here, where is, there it is. Take this term right here, and let's divide everything in numerator and denominator by n factorial. N factorial is never 0, so that's a legal thing to do, because n starting at 1, so it can't possibly be 0. So this would be the summation of n equal 1 to infinity of n factorial over n factorial over 2n factorial over n factorial plus 1 over n factorial. Okay, now this is all in the summation here. Okay, now I hope you see that has to be 1. I hope you see that has to be 1. And I hope you see that's got to go to 0, because n factorial gets big really fast. Okay, so it says that's going to infinity, that's going to 0. So what we have here is 1 over 2 plus 0, which is 1/2. That's how they got that. I thought that wasn't very fair of them saying, hey, this is what it is, okay, without telling you how. Okay, that's just the first part. What does that tell you, though? If the limit of the nth term is 1/2, what does that tell you about the series? Diverges. If it's not 0, it's going to diverge, and 1/2 is not 0. So therefore this one also diverges. So the limit of the nth term is not 0, the series diverges. Okay, here's one. For this series, summation of n equal 1 to infinity of 1 over n, we do have that the nth term is going to 0, because the limit is n goes to infinity of 1 over n is equal to 0. Is it time? Oh, how can it be? Okay. This is the one I was wanting to get to, though. This, just because the limit is equal to 0, does not guarantee it converges. It has, if it converges, the limit has to be 0. But that doesn't mean the limit being 0 guarantees convergence. And if you did this one, you would see that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. If you did that, this would be, the partial sums would be 1, 3 halves, and goodness gracious. My brain's not working well now. But anyway, it does not converge. This doesn't, because the limit is 0, the nth term test for divergence, the divergence doesn't apply. You can draw no conclusions about convergence or divergence. In fact, we'll see it does indeed diverge. Right now, all we can say is no conclusion. That's all. No conclusion. Whoa. That was example 5. We didn't have time to do 6. We'll do example 6. And guess what we're removing from there? We're moving to chapter 10. This is all we're doing in chapter 8. So we'll pick up next time with example 6 and move on to, and let me give you homework here. I'm sorry, I didn't want to cheat you out of that. Let me get rid of this. Okay. Homework here, any of the odds, again, do the concept check. Any of the odds 5 through 9, they're all at Calc Chat. 11 through 17, they're all at Calc Chat. 11's at Calc View. 19 through 23, they're all at Calc Chat. 19's at Calc View. 25 or 27, they're both at Calc Chat. 29 through 37, they're all at Calc Chat. 33's at Calc View. 39 to 43, both at all at Calc Chat. 39's at Calc View. 45 to 57, they're all at Calc Chat. 47's at Calc View. 59, you can explore doing that if you'd like. It should be at Calc Chat. 61 through 65 should be at Calc Chat. And then you can hang off for a bit and we'll pick up the rest of those next time. Okay? All right, we should finish 9.2 pretty quickly, and then we'll be going to 10.2. Not going to do 10.1, but 10.2. Now, what I haven't decided is I want to do a slideshow for you of the other sections here. What I think I'll do is leave those slideshows. I think I did it last spring. I'll leave those out there on the YouTube videos. If you want to see that slideshow, go there. Okay? Again, nothing was required, but we'll do that. So we are moving along here in chapter 9. Okay, well, almost through with 9, moving to 10. Now, it's going to take us probably another week at least, but that means get moving on your test. And I hope you're already moving on your research papers, right? Say yes. Okay. So please don't, take advantage of these weekends. Be careful, folks. The virus is still out there, okay? Be safe, be careful, get some calculus done, okay? Any last thoughts, parting shots before we leave? All right, take care, have a good weekend, and we will see you, see some of you later today, some of you tomorrow, but all of you I'll see on Monday, okay? Take care. Bye-bye.